Last time we talked about chemical reactions. Okay, and in a chemical reaction, you have reactants going to products. And moreover, when you had a chemical reaction with an enthalpy associated with it, we called it a thermochemical equation. And what we're going to find out today is that there's actually 3 ways to get that enthalpy of a reaction. And one of those ways is called Hess's law. And in Hess's law, the main idea behind that is that when you talk about a change in energy, all that matters is the initial and the final. And what's the difference? So likewise with a chemical reaction, we're talking about energy. Reactants that are such an energy, products that are such an energy. As long as you start with certain reactants and take who knows what path, it doesn't matter, but you end up with the same product, the change in energy will be the same. That's the idea behind Hess's law. I think we can visualize Hess's law with this weight. For example, let's take a look at the gravitational potential energy of this object. And you get gravitational potential energy just by the equation mgh, where you take the mass of the object times gravity times the height that you put it at. So right now, we're going to measure all our heights from the tabletop. So this object has 0 potential energy. If I put this object up here, now it has some gravitational potential energy, and we could calculate it with the equation mgh. Okay? What if I wanted to do the same thing, but first I put the object over here, then I put the object over here? What's the object's gravitational potential energy? It's the same answer we had before, right? It's just mgh. So what I'm trying to get at is the path doesn't matter, as all that matters is the beginning and the end. Well, it's the same way with chemical reactions. All that matters is the beginning and the end, the reactants and the products. The path doesn't matter. So like we mentioned earlier, there are 3 ways to get the enthalpy for a thermochemical equation. The first way we've seen already, where we calculated the heat. Remember, that was given symbol Q, and there are a couple ways to get it. We could use ms delta T, where S is the specific heat, or we could use C delta T, that is a heat capacity. So we used one of those equations, got our heat, divided it by the number of moles, and we got our enthalpy for the reaction. The second way is Hess's law. Let's take a look at how this works. You're given the below thermochemical equations. Use Hess's law to find the enthalpy for the reaction C going to D. Now remember, with Hess's law, the idea behind it is that the path doesn't matter. You just want to start with C, end up with product D. So what we're going to do is we are going to mess with these thermochemical equations they gave us. We can flip them, we can multiply them through by numbers, do whatever we have to do so that when we add them up, we get C going to D. And then we'll add up the enthalpies, and we'll have our answer. Okay, that's the game plan. So how are we going to do it? Let's take a look at the reaction number 1. What should we do to the first one? Should we flip it? If we multiply it through by 6, what? Notice how, if I clean it up a little bit, C is on the reactant side. C is on the reactant side. The stoichiometric coefficient is 1, so don't mess with it. Just write it as is. A plus C goes to B. Delta H is positive 200 kilojoules. Don't do anything to reaction 1. Reaction 2, D has to be on the product side with a stoichiometric coefficient of 1. That means pretty much just flip reaction 2. So we'll have B going to A plus D. And our enthalpy is a positive 300 kilojoules because we flipped it. Now if we did this right, everything should add up and we'll get the right answer. Notice my B's cancel, my A's cancel. I end up with C going to D. Looks great. And my enthalpy, just add them up. 200 and 300, 500 kilojoules. So 500 kilojoules is my enthalpy of the reaction C going to D. Here's our third way to get the enthalpy for a reaction. We're going to use tabulated values of this symbol. This is called standard enthalpy of formation. So for every reactant and every product, we're going to look up its standard enthalpy of formation. And all we do is we plug it into this expression. All the enthalpy of formations of the products minus the enthalpy of formation of all the reactants, and we get our answer for the standard enthalpy change for the reaction. It's kind of neat how they do this. Let's take a look at carbon dioxide gas. We could look up its standard enthalpy of formation. It's some number, right, in a table. But how did they get it? What they did is they took its elements in their natural state. So the elements of carbon dioxide are carbon solid and oxygen gas. And they formed carbon dioxide gas. What was the enthalpy change for that reaction? That's the standard enthalpy of formation for any compound. It's always formed from its elements. And the reason why this works is because they said, hey, all elements in their natural state have a standard enthalpy of formation of 0. So that means carbon solid, standard enthalpy of formation is 0. Oxygen gas, 0. Any element in its natural state, just how it occurs in nature, its standard enthalpy of formation is 0. So that's how they got tabulated all these standard enthalpies of formation for all these different compounds. They just synthesized them from their elements in their natural states. So let's try this. Calculate the standard enthalpy change for the reaction. 2 moles of lead sulfide combines with 3 moles of oxygen to form 2 moles of lead oxide and 2 moles of sulfur dioxide when given the following. So we don't have that whole big table. We just have the numbers that we need. So we apply that expression, the standard enthalpy of any reaction. Take all the enthalpy of formation of the products minus the enthalpy of formation for all the reactants, and we'll have our answer. So we need 2 lead oxide, it's negative 219. And we have 2 moles of sulfur dioxide, a negative 296.8. Minus the reactants enthalpies of formation. 2 moles of lead sulfide, negative 98.3, and 3 moles of oxygen. Now, oxygen is in its natural state, so it's 0. So they're never in the table. 219 negative times 2 plus 296.8 negative times 2 plus 2 times 98.3, get about negative 835 kilojoules. You can write the per mole if you want. Find the change in enthalpy for the below reaction by using the below thermochemical equations. So this is a great example of Hess's law. We have 3 equations. See what you got to do to each thermochemical equation so that when you add them up, you will get this answer. So that should match down there. Try it. So in the first equation, I want to flip it because I have this compound as a product. So I'm going to have to flip it. So that means I'm going to have 2 moles of carbon dioxide and 2 moles of water forms 2 moles of oxygen. And I flipped it, so my delta H is a positive 874 kilojoules. Now the second reaction, notice that I've got a C graphite is on the reactant side, and I've got a 2 in front. So I'm going to take this times 2, but don't flip it. So I'll have 2 C graphite and 2 moles of oxygen forms 2 moles of carbon dioxide. And I need to multiply 394 times 2 is negative 788 kilojoules. Now take a look at the third reaction. What should we do to it? I see that I have no water. There is no H2O in that reaction, right? If there's no water, I better get my waters to cancel. So if I'm going to get my waters to cancel, I need to multiply this one through by 2 so I can cancel the water. So if I multiply through by 2, I'll have 2 hydrogens and 1 oxygen forms 2 waters. Multiply through by 2, a negative 286 times 2 is a negative 572 kilojoules. So if I add this stuff up, let's see if I get the right answer here. These 2 oxygens cancel with those 2. These 2 waters cancel with those 2 waters. Those carbon dioxides cancel. I think it worked out, because now all that's left is 2C graphite and 2 moles of hydrogen and a mole of oxygen forms this compound. It matches. So all I have to do is add up my enthalpies. 874 minus 788 minus 572, a negative 486 kilojoules. There's my answer. So negative 486 kilojoules is the enthalpy for the reaction that they wanted. What is the heat of the reaction at constant pressure for the below reaction? And use the below thermochemical equations. So don't let the idea of constant pressure confuse you. Enthalpy, all enthalpy changes have to happen at constant pressure. It's assumed that pressure is constant when you measure these heat transfers. So don't really worry about that. So we have 3 equations. According to Hess's law, we can get the enthalpy of this reaction, and the steps don't matter as long as we start with these reactants and end up with those products. So try it. Manipulate those thermochemical equations and add them up until you get the right answer. The reaction 1, I want to flip and divide by 2 because I'm looking at that ammonia. It needs to be on the reactant side and a 1 out front. So if I flip it and divide by 2, I'm going to have NH3 goes to 1/2 nitrogen and 3/2 hydrogen. And if I flip my delta H, negative 91.8 becomes positive 91.8. Divide it by 2, I get 45.9. For the second reaction, I see I have methane. I want that on the reactant side, so I'm just going to flip it. So I'll have methane goes to C graphite and 2 moles of hydrogen. And I just flipped it, so that's a positive 74.9 kilojoule. In my third reaction, I see in my answer there's no C graphite. So I want to get that C graphite to cancel out. So how can I do that? I'm going to have to divide it by 2. So I'll have 1/2 hydrogen and C graphite and 1/2 nitrogen goes to HCN. So I divide 270.3 by 2, I get a positive 135.15 kilojoules. So if I add everything up, let's see if this works. C graphite canceled. My nitrogen is gone. This half hydrogen will combine with one of these. I'm just left with a 1. So 1 and 2 would be 3 hydrogens. I think it's going to work. Let's try it. All my products, I'm going to have ammonia. It's going to form 1 hydrogen and 2 hydrogens. That's 3 hydrogens. So 3 hydrogens and my HCN. It matches. Great. So I'll just add up my enthalpies. 45.9 plus 74.9 plus 135.15, about 255.95 kilojoules. There's my heat of the reaction for the thermochemical equation that they wanted. Obtain the standard enthalpy for the below reaction. And they gave us all of the standard enthalpies of formation for everything that we need. So great, let's just find the standard enthalpy of the reaction by taking our products minus the standard enthalpy of formation of our reactants. We have calcium, a negative 543, and 2 moles of bicarbonate, 2 times a negative 691.1. Our reactants, calcium carbonate, a negative 1206.9, and carbon dioxide, a negative 393.5, and water, negative 285.8. A negative 39, and it's kilojoules. So the idea with these enthalpy of reactions is essentially there's 3 ways to get the enthalpy for a chemical equation and turn it into a thermochemical equation. The first way we talked about earlier, where we divide the heat by the number of moles that was either produced or reacted. The second way is Hess's law, where remember the path doesn't matter. All that matters is where you start and where you end up. And you can take whatever path you want, as long as you start and end up at the same place, you get the same energy. And our third way was the same idea, except we use these tabulated values of standard enthalpies of formation for every reactant and product. And then we took the enthalpies of formation of the products minus enthalpy of formations of the reactants, and we got the standard change in enthalpy for that reaction. And just remember, all elements in their natural state have standard enthalpies of formation of 0. Good luck.